Okay, hello everyone. Today our group will present you the topic of the project is imaging painting via cellular automaton, and here you can see the whole people in the group, and our TA is Ruslan Rahimov. So in this slide you can see the structure of the presentation. We will start from the problem and then we will tell about our solution and experiments and show the results. Okay, let's move on. And imaging painting problem. So recently, Google researchers represented a thread of papers devoted to the application of cellular automata, and we decided to understand it and use the approach of cellular automation on the imaging painting task, which was never used before in the given task. From reviewing previous works of imaging painting problem, three main approaches were noticed. It's a patch matching using CNN and GAN architectures. And we were curious on the last two approaches, since from the Google researches was noticed that cellular automation update rules can be done by usage of convolutional neural networks. And in addition to this, as one of the popular approaches of such problem, we proposed to try a creation of GANs using cellular automation as a generator of images. Okay, on this slides you can see some practical application of the cellular automation, which were presented in the Google series of articles. And here you can see grown cellular automata, which is shows how image can be reconstructed from the pixel and self-organizing textures, which used cellular automata too. Okay, let's move on. And here you can see that cellular automata was also used for solving image segmentation problems, and this article was actually used as a basis, as a basic idea in our model architecture. So here you can see the architecture, and here each cell is described by a 48 dimensional state and contains 4 hidden layers. Inside the sequence of hidden layers, we used a state of size 32, and the first convolutional operator uses transforms from 48 to 64 channels, and the first layer in the sequence is a 3x3 convolution, and then the remaining layers are 1x1 convolutions. And the predictions is obtained by applying an additional 1x1 convolution. Then we use the ReLU for all hidden layers, and we used in our experiments standard Adam optimizer with the learning rate 3.10⁻⁴, and the batch size was 128. Now let's talk about our experiments. And firstly, we used two popular datasets, which is the MNIST dataset of images of digits, and Celeba dataset, which contains 200,000 pictures. Okay, we use these datasets. So let's move on. Then we tried different types of mask patterns, which is a quadratic, rectangular, and freeform mask, which we called a brush mask. And here you can see the representation of the masks, how they formed and how they applied. Okay, and we use the mask as the input parameter of the model. It helps model to train and imitate the losing of the part of the image. Each type of mask is used for training and for validation. And at first we need to choose the mask type. After that, our mask will be randomly created with different coordinates and so on. We do not fix it in advance. And we train our model, and after that, we just get the results. And a few words about trained parameters. We have 5 epochs, and each epoch was trained for 15 minutes, and the main parameters you can see on the slides. So to obtain the best results, we used different tricks. Like for instance, we used some iteration without loss and with losses. We used two hyperparameters devoted to the number of cycles with losses and to the number of cycles without loss. It means that first we train our N1 batches without loss and N2 batches with adding the loss to evaluate the stability of model training. So the another trick we used is Bernoulli distribution to decide update the model or not. The Bernoulli variable randomly disables changes to the cell to simulate asynchronic evaluation of different cells. And here you can see the results of our baseline. Okay, let's move on. And here you can see the reconstruction of the image by the iteration. And we see that like good results are obtained in the iteration 21 and 18. Like 21 is like the best reconstruction of the image. Okay, let's look at how rectangular mask influence the results. And here we can see like the rectangular mask and here the brush mask. And here we can see that applying the rectangular mask, we don't have really like the same images as we have in original one. And here you can see that the reconstruction wasn't good. However, when we use a brush mask, which is surprisingly, we see that the reconstruction is almost the same as the original image, which just results in the fact that the brush masks are better choice. Just performs better than the rectangular mask. Okay, let's move on. Here, another observation that we saw that eye reconstruction is very complicated since the structure of eye is complicated. And here you can see that when just the half of eye is masked, we can be reconstructed. However, if we have the reconstruction of we need to reconstruct the whole eye, we can't do it. And there were some outliers like sunglasses, which is represented here, which also couldn't be reconstructed well. Okay, then we just checked the different types of loss. We checked L1 and MSE loss comparison, and here we just obtained the result that they are almost the same, and we just proved that they are like in the same nature. Here, like the another results of experimenting L1 and MSE loss, and to estimate the image quality assessment between original image and our reconstruction image, we used two metrics, which is a structural similarity index measure and peak signal to noise ratio. And here you can see the results. And we see that the reconstruction using L1 loss and using MSE loss is almost the same, and they work both well, which just proves that we can just choose any of it, and image reconstruction is good. Okay, in order to improve our model, we decided to use more complex architecture, and we decided to use GANs, as I said previously. Here the GAN pipeline of and here the generative adversarial network consists of two different models, which is the generator and discriminator. And as a generator, we put our previous model, and we just add the discriminator and try to improve our results. However, here you can see what we got, the final results, and we can see that our model baseline work better than the GAN. However, it's result 2, and here you can see that the results on the MNIST dataset. So to sum up, we conducted a series of experiments with different types of masks and losses, and in fact, we found out that our model has equally good results with all used mask types and with different losses which have the same, like as the same value. And for all experiments, we used different data sets. And in fact, we found out that our baseline model has the best result comparing to GAN architecture, which doesn't improve our model as we expected. However, we tried to improve it. We used DC GANs. We tried to remove batch norms and add a spectral norm, but it didn't yield good results. Now we just can make some decisions or suggestions of how to improve the results, like for instance to increase the batch or to use more complicated kind of architectures. So thank you for your attention. This is it. Bye.